Lesson 14.5, calculating pH, weak acids. And there's several problems I want you to do. There are a lot of problems on the paper that you don't have to worry about. I'll talk a little bit about some of those. There's one on the worksheet that you're not even required for AP, but number 2, number 48, 7, 8, and 54. Some of those came out of books. That's why that's why you see those big numbers that were scanned. Okay, now you'll probably like this a lot because really, if you're pretty good with your equilibrium, if you remember that from the other chapter, you're just going to add pH to equilibrium, and then there's some different kinds of calculations you can make from it. All right, so I'll start off by doing the very first, just starting right off with the calculations here. In calculating pH, weak acids require more considerations than strong acids. Well, basically, if you have a weak acid, you have to go through the equilibrium icebox procedure, or I'll call it that, in order to find out what the pH is. Okay, it says, calculate the pH for a solution that is 1 molar HF, hydrofluoric acid, hydrogen fluoride. For you would call it hydrofluoric acid. When it has a molarity in front of it, you call it acid, hydrofluoric acid. If it were just HF, that would be hydrogen fluoride, like pure hydrogen fluoride, which I don't know, it's probably likely a gas. Anyway, pH of 1 molar HF. All right, so this is 14.5. And it says A. So, now, these problems, either I made them or got them from the book or somewhere, but they're not written the way the AP exam would have you do it. First of all, for the AP exam, they either give you the equation or they might ask you to write the equation, how HF reacts with water. Maybe for this one, I'll do the water method, the water equation method. Hydrofluoric acid would react with water to give you, or hydrogen fluoride gas would react with water to give you H3O plus and F minus 1. Gotta fit it there. I'll put F minus. Okay, so as you see, water takes the H to make H3O plus. There it is. That's your hydronium. Now, it says you have 1 molar hydrofluoric acid. So I'm going to put, you're going to start with 1 molar. Well, that's your initial icebox. 1 molar. Okay, what's the pH of that? So icebox, I-C-E. Now what I'm going to do is say, initially, when it says this, what's the pH of 1 molar HF? Well, really, it's not going to be exactly 1 molar HF. Because as soon as it's in water, it might be 0.999 or 0.998 or whatever, however much it dissociates, will be the actual molarity, what you have there. Because if it, anyway, so whatever molarity they give you initially, you put it here. At equilibrium, it'll be slightly lower. You're going to subtract something from it. But it doesn't matter. Because weak acids are so weak, you can pretty much consider that is the molarity, 1 molar. All right, now, we know that you start off, we'll say at first there's none of this at all. So maybe it is like a gas going into water or something. It could also just be hydrofluoric acid diluting it more with water. Now, the change will be minus X, plus X, and plus X. We don't have to worry about water, the change in the amount of that, because there's so much of it, we don't even look at that one. 1 minus X at equilibrium, X and X. Now, a lot of these, as you do these over and over, you'll be tempted to say, I don't need to do that, to take shortcuts and not make an icebox. And if you're really good and sharp with it, you could, but I would not recommend it ever. I would always recommend you do an icebox. Even if you do an icebox and you abandon it, you're like, oh, I don't need it now. It's okay, it won't hurt you. They don't require the icebox. So, but when you get later on down the line to what's called KSP, you'll want to have that icebox. You remember I've shown you some of those before already, because otherwise you could really make a big mistake if you try to do it all in your head. Okay, now, so normally they'll say write the equation and how hydrofluoric acid reacts with water, all right, to dissociate or whatever, or, you know, that would be what you write. You could also, they might say write the K expression, the Ka expression, and so you know only the aqueous substances. So water is the liquid, everything else is aqueous. In the acid equilibrium, the acid will be aqueous. This will be aqueous, and this will be aqueous. Now, if they had said hydrogen fluoride gas, they're not going to say it on this problem. But if they ever said hydrogen fluoride gas, then you put gas there, and it wouldn't be in the Ka expression in that case. But they're not going to do that to you. Believe they're not going to do that. Okay, here we go. So for Ka, it's going to be H3O plus and F minus over HF. And I'm going to show you a shortcut way on another problem. I'll do it without the H2O, H3O. Okay? So it says the Ka value is 7.2 10 to the negative 4. This ought to be kind of familiar. H3O at equilibrium is X. F negative is X. And then it's 1 minus X. Now, for this one, let's see. What we'll do is you can assume X is negligible. So then that means 7.2 10 to the negative 4 is equal to X squared over just 1. Now, if you want to keep it X time, I always tell you that when you assume X is negligible, you could jump to X squared. But anyway, what all that does, it removes anything you would subtract. It removes the change, the minus X, or if it were minus 2X or whatever that would be, or plus X. You're not going to have that on these. Now, all right, now that's easy. 1, so 7.2 times 1 is 7.2. This is a pretty easy one. Equals X squared. You get the square root of both sides. So the algebra is easy on this one. And it's going to be the square root of 7.2 10 to the negative 4. 0.0268 equals X. Now, they ask for the pH on this one, but sometimes what they can also ask you is, well, on the questions, your textbook does it, but AP will be more specific about it. But the textbook says, well, tell the molarity or concentration of all the species that are present, in the mixture, in the equilibrium mixture. So all the species would be like HF, H3O plus, and F minus. The textbook even says to put OH negative there. There's a problem on the worksheet you might find like that. When you look down the answer key, if it says OH, go on and find it. But on AP, I think they'll be specific about that. They'll say, like, find the H plus, the OH negative, and the F negative, or the HF at equilibrium, or H3O plus. So HF, H3O, F negative, and OH negative. All four of those. H plus is the same as that one. So this, first of all, this molarity is equal to X. So that means it is H3O plus. So you can say that equals X. So that also equals the H3O plus concentration. All right. That also equals, in this problem, the F negative. So you can say F negative is also 0.0268. But then to get HF molarity, it will be 1 minus 0.0268, because 1 minus X. Now, they didn't ask you on this problem to do all this, but I'm just telling you how you would do it. The same as we did in the gas law and all, the gas equilibrium chapters. You just find those three things. In fact, you could do it right under it if you wanted to. Just put X, put the number there, the number there. But I'll do it here. So 1 minus 0.0, let's double check it, 0.0268, so it's 0.973. So see, the HF at equilibrium is really 0.973 molar, and the other part is what's the pH of that. Okay, so now let's do the actual question. What is the pH? Well, this first I told you all the molarities of everything. H3O, F negative, and HF. Oh, if they wanted OH, hold on, I'll do that one too. If they wanted the OH, then you would go to the equation. H3O times OH negative gives you 1 times 10 to the negative 14. All right, it could be 1.0, yeah, times 10 to the negative 14, right? Was it right about that? Or could it be 1.00? I can't remember. It's 1.0. It's 1.0. Yeah. Okay. So, if I put in H3O 0.0268 times OH negative, I don't think it was 1.00. Now the pH can be 2 O's. Right. The pH can be 2 O's after 2 places at the decimal. So 1 times 10 to the 14 negative divided by 0.0268. OH negative would equal 3.7 10 to the negative 13. Okay, so if you were ever asked to find the OH also on this problem, well then that's how you would do it. You find the H3O, you do it. But again, I'm doing all these extra things to maybe save time on some other problems in case you see it. All right, now the important one is find the pH. So let's do that one. That's the main question. So if that's your H3O, just remember that pH is the negative log of the H3O plus concentration. Negative log of 0.0268 and 0.0268 log. And so all I do, and I think I've shown you on the other video too, but 0.0268, and on this calculator, there it is, 0.0268, I'm going to push log, and you get this, but you get a negative number, so you got to make it the negative of that. That's why negative is in the symbol, so make it negative of negative 1.57. And then the other thing is watch your sig figs. Remember, the molarity has a normal sig figs. All right, it has 3 sig figs. You can normally do it all year. But 3 sig figs here, you start counting after the decimal. So 1.572 will be the pH. Alrighty, that's the whole thing. Now, if you know, I did show you percent dissociation, and I'll do it on another problem. But I showed you that I think in the past on another problem. I think I did. And if you know percent dissociation and you know everything I just showed you, some of you could already do all the homework. Well, maybe not. I'll gotta show you a couple things. I gotta tell you one more thing. But some of you could almost do all the major stuff right now. I just remembered there's one thing I gotta tell you about, and it's not even. It's very simple. It might be the next one. Okay, so the next part of the note, steps to follow. I wouldn't even really worry about that. The book does this. They outline the book. Many years ago, I mean, it was 15, whatever, maybe longer. I think it was 20 years ago when I was preparing to teach AP. I made all these notes from the book, and I thought, oh, I better tell them this. I better tell them everything here. No, the book, AP just doesn't have you. They're not going to give you a problem and say, find everything. They're going to ask you step by step what you need, so you don't really have to go through those steps. I mean, they're not bad to look at them, but okay. But let me go to the next one. Hypochlorite. Calculate pH of 0.1 molar, 100 molar aqueous HOCl. You know what? I won't even do that one. It's the same thing we just did. There's nothing different about that problem. The only thing I'll say, well, I'm not even going to. Well, yeah, I'll just tell you one thing about that if you wanted to. When you write the equation for that, you could also write this. HOCl just breaks down into HF, H plus, and OCl negative, and do your icebox, and that will be your hydronium. Instead of having H2O and H3O, you can also just put nothing here and just break it off H plus and OCl. Same way, the problem I just did, I could have done my icebox like this. And what happens is, usually the AP gives you the equation you need on the equilibrium problem. You don't even write it. If they do ask you to write it, they probably are going to ask you to write it plus water. Like HCl plus H2O gives you H3O plus OCl negative. But that problem is done the same way as the other one I just did. There's no need. And you can just do, you might even see one, you will see one just like that on the homework. And then you'll see the answer key later, so there's no need for me to do that problem. All right, 14.5b. Okay, calculating pH for a mixture of different acids. I do not see this on the AP. I've looked through. Here's what they could do. They could ask, I'm going to tell you how they treat it. It says a solution is made of a mixture of acids. A solution prepared from a mixture of acids is 0.100 molar HNO3 and 0.100 molar HOCl. Okay, calculate the pH of the solution. All right. This is the AP little shortcut of this. I don't see this happen very much at all. But, and maybe it's more like on a multiple choice question or something. Or it could be, it could be like a question where there's A, B, C, D, E, and it could be a little small part. What if you had a mixture of these two things? Well, here's the deal. First, you need to immediately recognize that's a strong acid. And guess what? The strong acid wins. If I did an icebox with this, it's going to be so small. These are both going to cause, like if you have both these in a solution, they're both going to cause H plus to be in the solution. We know that. But the amount that contributes is so small compared to what that puts. In fact, that even hinders this a little bit because there's so much H plus that it's kind of like, I don't know if I've gone over that yet. Did I do it in the last? I didn't do what's called the common ion effect. I'll talk about that later on. But it actually, the HNO3 has so much H plus, it actually causes some of this to not break up as much as it would. So all you need to know is the strong acid wins. Now, I did a problem. I didn't do it for you, but I told you how to do it in the last video, and there was one on the worksheet. If these were two strong acids, like 0.100 molar M and 0.100 molar HCl, then I'd have to they give it volume 20 milliliters, 20 whatever it is. You'd have to find the moles of this H plus, moles of this H plus, add the H plus, total moles of H plus, divided by total volume. You'd have to get the molarity. If you had two strong acids, you'd have to calculate all the stoichiometry, find all the H plus from this one from that one, add it together, get your total moles of H plus on top, and divide by your total volume. You've got to be very careful to read that. That's your molarity. Now, you'll assume that molarity is your H plus, and you'll find the pH, the negative log of that. If you have two strong. Now, if you have a strong and a weak acid, you can just ignore the weak acid. You said the strong acid would dominate. You can just write that. Strong acid will dominate. So the amount of H plus from this is negligible. The H plus contributed from that will be negligible. All right. So here we go. So if it's 0.100 molar HNO3, I would write that. Strong acid will dominate. H plus from HOCl is negligible. In fact, it might be good to write that down if this ever happened on the AP. I think it's more likely to see something you'd see on a multiple choice, but oh well. Okay, and that might. Okay, here we go. So all you do is pH. So assume H plus will equal the HNO3 molarity, which equals 0.100 molar. So pH is equal to negative log of 0.100. So it's going to be 1. 0.1, push log, and it's going to be 1, and you get to have 3 sig figs, 1.000. Very acidic. All right. 1 in the pH scale. All right. That's all you have to do. So now, okay. All right. I'll tell you the next thing, and just so you need to know, D, an aqueous solution has 1 molar HCN and 5 molar HNO2. Both those are weak acids, and I never see that on the AP. So it's beyond what they're going to ask you for AP, so we're not even going to do that, and I'm not going to ask you about that at all. You can skip D, forget D all the way. All right, so we will jump to 14C. So at this point, if you're really... Many of you could already do the whole worksheet right now, probably. Many, if you're like, if you've been keeping up with all the lessons. But I want to show you other ways. There's a little things here that there are different tricks to it. I don't want to say I said that already. I already said it. But if you're really sharp with everything, I'll say, oh, I got that down. This will be easy. But you better watch. Okay, 14C, percent dissociation. I already told you about this. That let me just see. Actually, there's a whole lot of notes here. And again, a lot of this was copied right from a book when I made it. Just kind of like, I always thought it would be kind of important. It's not a bad thing. I'll kind of summarize it in a moment. I'll go back over that. But let's go down to the next D. Calculate on the next page. D and E are there. D says calculate percent dissociation of acetic acid. Yeah. Okay, I got to do a lot of these problems. So D, calculate percent dissociation of acetic acid in the following solutions. All right, and we've got 1 molar and 0.100 molar CH3COOH. All right, so for that one, I guess I'll even do it with a shortcut for this one too. H plus and CH3COO negative. Now, I'll just go on and do it twice, I guess, or I'll set it up. Because what they're doing here, they're asking you to compare. They want you to find A and B and then compare them. I don't usually like to ask something like this on quiz or test so much because it's kind of time consuming. And I think in the time that you do 2 ice boxes in one problem, I could have asked you 2 different problems, like an acid and a base, and that's, to me, that's more valuable. AP, they could do that on AP. They have done it before. Where you had to do like 2 ice boxes. And, you know, if they do that, they know, they take that into consideration for how much time. Like I say, when you work an AP problem, a giant problem, A, B, C, D, E, like the kinds you see if you go to the AP readiness, you should be able to do an A, B, C, D, E, or A, B, C, D, E, F, and they even have part 1, 2. You ought to be able to do that problem in at most 20 minutes. 15 to 20 minutes, you should be able to do it. So if they give you a problem with this on there, a person should be able to do it in 20 minutes. But they have to really know what they're doing and all that. I don't think... Okay, but anyway, here I go. I'm talking so much about it. 1 molar and 0.100 molar. So if I have 1 molar, then I have 0.100 molar. 2 different situations. They're both going to be 0 to start off with. Minus x plus x plus x. 1 minus x, x and x. Looks like this is the one we just did, doesn't it? 0 and 0, minus x plus x plus x. 0.100 minus x, x and x. So 2 little ice boxes. And then my Ka, I'll try to write a little smaller and fit it on here. Ka equals H plus, for both of them, CH3COO negative over CH2. This is the form of Chaku, which they sometimes use for acetic acid. Oh, I could have done one way and one the other. I didn't think about that. Oh well. All right, now, for acetic acid, I just know it. It's 1.8 10 to the negative 5. Actually, it's on the problem before it. But 1.8 10 to the negative 5 is a Ka. So what will be the percent dissociation? So at equilibrium, it's x and x over 1 minus x. Well, for this problem, I don't know if it fits down this low. 1.8 10 to the negative 5 equals x times x over 0.1 minus x. All right, I don't know if I have space to get all of it on there, but okay, so first what I'll do, assume x is negligible. For both of them. I wrote it twice. If it's on the same problem. All right, now 1.8, I would spell it out. Neg, glee, g, bleh. All right, 1.8, 10 to the negative 5. That's going to be x squared over 1. That's going to be 1.8, 10 to the negative 5 equals x squared over 0.100. What a mess I've got there. Can you even read all? Yeah, I guess you can see that nastiness. Okay. Assume x negligible. Like I said, you don't even have to have proper English. Assume x negligible. They'll know what you mean. Okay, 1.8 10 to the negative 5. Don't show your AP, English teacher that. Okay, 1.8 10 to the negative 5 is x squared over 0.100. So 1.8 10 to the negative 5 times 0.100. 1.8 10 to the negative 6 to get the square root of that. So x, for this one, x equals 1.3 10 to the negative 3 molar. For this one, 1.8 10 to the negative 5 times 1, that's the same number, just get the square root. It's 4.2 times 10 to the negative 3 equals X. I just realized that's something I should tell you. I'll do it here. Okay, so this, what you found is the molarity of H plus right here. That is the H plus molarity at equilibrium. And this is the H plus molarity, H plus at equilibrium for X. Oh well, I'll put H plus. All right, 1.3 to the negative 4, 4.2. Did I do all that right? 1.8 to the negative 5 times 0.1. Yeah, 1.3 to... Oh, wait. 1.8 to the negative 5 times 0.1 square root 1.3. Yeah, I did. 4.2 to the negative 3. Yeah, you're not with me, so I have to do this to make sure. Negative 5, 4.2 to the negative 3. Yeah. Okay, so to find if I wanted to find the pH, then it would be, negative log of that. That's not a big deal, but they're not asking. There's not asking that right here. All right, here's the deal. Here's what you need to notice. This problem was 1 molar, and 1 molar means that you have a whole lot more of this. Okay, a whole lot more of the acetic acid. Here you have less acetic acid. You have less point. It's more dilute. You might say more diluted. Okay. So watch this. If I take this and divide it out, to find percent dissociation, I'm trying to find somewhere I can write it that won't be a mess. I'm going to probably have to erase the ice box there. So yeah, remember, well, I'll erase this one. And then it's okay. We started with we've got to remember the initial was 0.100. Initially it was 0.100 molar. Okay. Here is the equation I think I've shown you before, but percent dissociation equals the H plus that you have at equilibrium. How much H plus broke off divided by the acid initial times 100. So at equilibrium, X, you had 4.2, 10 to the negative 3. And you started with 1 molar times 100. So 4.2, 10 to the negative 3 times 100 is 0.42% dissociation. Now for this one, the other problem, the original H plus, the H plus at equilibrium is 1.3, 10 to the negative 4. But on that one, your original acid, HA, HA in this case, you could also write acetic acid as HC2H3O2. HA, that's your anion. So here's kind of like AH, that's your anion, H3CO, negative 1, H plus. But anyway, it's still HA. But the acid in this one was 0.100 times 100. So 1.3 to the negative 4 divided by 0.100 times 100 equals 0.13%. Okay, so 1.3 to the negative 4, making sure I did the math right. All right, 10 to the negative. Oh, I'm sorry about that. You know what? That is 3. I did make a big mistake there. Wait, 1.8 to the negative 5 times 0.1. Maybe I didn't see the little thing erased there. 0.1. Didn't get the square root of that. Yeah, that should have been negative 3. I'm sorry. Some of you have been yelling that, I know, the whole time. Vela, it's negative 3. Vela, you've been hitting the whatever, your iPad or iPhone or whatever you got there. Okay, that's going to change things. 1.3 10 to the negative 3 divided by 0.100 times 100. 1.3%. That's your percent dissociation. Now, so percent this equals 1.3 over 0.100. Now here's an interesting thing that I just want you to know or to see. Notice in the first chemical, in the first solution, it was 1 molar. Okay? 1 molar means a whole lot of chemical in the water. But down here, in this problem, it was only 0.100 molar of the acid. So why does that matter? Think about this. Who is outnumbering in each solution? Is it the acid or the H2O molecules? In this one, you have a lot of acid. Well, water molecule, I shouldn't say outnumbering. Water is always going to outnumber it. But who has more water molecules in ratio to the acid? And that would be in this one. In this one, you have a little bit of the acid molecules, and a lot of water molecules can all say, oh, let's jump around them and all that. But here, there's a lot. There's not as many water molecules are able to surround them. That's another way to look at it. Imagine that these acid molecules are like some famous celebrity. You know, they say if they walk into a Costco or somewhere, everybody's going to crowd around them like that. Think about everybody in Costco. We're just water molecules, okay? And then somebody famous walks in, and they're going to be like this acid or something, and you're going to all go around them and try to, like, just say you're trying to go in, or maybe it could be it could be like a group, like a 4 or 5 musical group, people famous, you know, they walk in. So everybody crowds around all the members of the group like that. Like water molecules will crowd around these acid and separate them out and stuff. Well, what I'm trying to get at is, in this condition, in 0.100 molar, you have a whole lot of water molecules and just a little bit of celebrities. But here you got a lot more celebrities. So water is going to do a better job of surrounding the celebrities in this one. Okay? Now, why does that matter? Because if water molecules are better at surrounding them, then you have a higher percent dissociation, 1.3 compared to 0.42. So here's an easy way to look at it. If I give you an acid, a drink, well, like lemon juice, whatever, a drink of acid, and you taste it sour. If you add more water to it, or if you make it more dilute, it will actually become more a greater dissociated. All the molecules will break up better and better. So you'll have a higher percentage of them will dissociate. Okay, I'm just talking so long here. All right, I think I got 1 or 2 more problems to show you. I might go through both of them because this is such an important topic. So, still in 14.5. I don't know why I erased that. Okay, E is about lactic acid. Oh, and then there's one more after that. I need to do both of them, really. Okay, so, all right, E. It says, lactic acid, this is kind of interesting, is a waste product that accumulates in muscle during physical exertion. So when you exercise, whatever it is, and you start to get tired, what's happening is your muscles are producing lactic acid. And when your arms get tired and like that, they're getting acid, and that makes you not want to, I can't move my muscles anymore hardly. Okay, it could be pain and fatigue, at least pain and fatigue. In a 0.100 molar aqueous solution, lactic acid is 3.7% dissociated. Calculate the value of Ka. This problem is kind of backwards. They're giving you the percent, and now they're going to say, what's the Ka? They didn't tell you the Ka. So, for lactic acid, I'll start off with HC3H5O3. And I guess why not? I'll put water in this one, H2O. To give you, I picked a good one to do that on, didn't I? Gotta have space for that. All right. Lactic acid. C3H5O3 plus water, H3O plus, and so just take the H away, what you're left with, C3H5O3, and it must be -1. I think I did tell you, or if I didn't, that every acid on the AP is always a +1, +1, -1. You never have to worry about a polyproduct, diproduct. You'll see those in the notes. I'll talk about it later on, but we're going to pretty much skip it. Okay, they stopped asking about that. So here we go. All right, so icebox. It says you have 0.100 molar. So we've seen this, like, wait a minute, isn't this the same problem? -X, look at that. I'm not even really thinking or reading the question yet. I'm just doing this already. And that's that's okay. You might do it so quick, like you're programmed, and then you realize, I don't need it, but you do need it for this one. Okay. In that solution, lactic acid is 3.7% dissociated. Okay, I can even go on and do my Ka and put the lactic, I guess that would be lactate. So even on the AP exam, if you see some acid, like I've never seen that before. What is that? You know, HC8, H5O9O3. What is that? I don't know. It doesn't even matter because that will break up into H plus or H3O and HCH5O3 negative 1. That might not even exist. But don't be afraid. They like to give you things on AP that no one has seen, just so you will to see if you know how to handle it. Okay. And sometimes, I know I write -1. A lot of times they just put a negative sign there. Okay. So we don't know the Ka value. That means we got to figure out some of this stuff down here. So maybe, yeah, I think it is important to have the icebox. You might say, well, I don't really need it, but okay, I'll show you. Here's the great information they give you. It is 3.7% dissociated. So what that means is 3.7% of all of this 0.100 breaks up. That's how much breaks off. So 3.7% times the, I'll make it brackets, times the HA initial will give you the H plus at equilibrium. How about that? So the percent times the acid original molarity will tell you what the H plus is at equilibrium. Look at that. So, of course, you make a percent means, per 100. That means 3.7 over 100, porciento por divided by 100. So all I'm saying is change that into a decimal. There's no 0 after it, is there? 3.7, no. Okay, 0.37 times 0.100 molar will give me the H plus at equilibrium. So that's going to be 0.00. Yeah, 3.7 times 10 to the negative 3 equals the H plus concentration at equilibrium. Okay, now here's the deal though. So they have given you this. 3.710 to the negative 3 is H plus. Well, H plus, I could have put H3O plus there. I'm sorry. Either way, it means the same. You've got to know it's the same. So that means that this is 3.710 to the negative 3. Let me, since I squeeze it together so much, I'll use another color. That's 3.710 to the negative 3. That would also be the same because it's also X. And this will be 0.100 minus, well, I might write it like 0.100 minus point, what would that, 0037. 3.710 to the negative 3. 1, 2, 3. Yeah. So it's good to know how to change the scientific notation. Sometimes when you're doing a problem, especially if it were a multiple choice problem, but if you're trying to do a problem, sometimes that makes it easier to kind of see how you subtract it. So 0.1 minus 0.0037, 0.0963. That should make, that makes sense. 0.0037. Yeah. Okay. So at equilibrium, that's your lactic acid molarity. That's your H3O or H plus molarity. That is your lactate molarity. Plug them in over here and you'll have the Ka. So H3O, 3.7. So we didn't need to do any assume X is negligible in this problem. Well, I mean, you can see, well, I said it before I showed you, but because nothing's unknown. So some people would say, you don't really need an icebox. I would say, yeah, you want to have an icebox to go back there and know to plug those numbers, to find those 3 numbers in. And most likely, I'll look at the answer first. It looks like I got 1.410 to the negative 4. Let me do it again. 3.710 to the negative 3 times itself divided by 0.0963. 1.410 to the negative 4. I hope I didn't do anything crazy with my math. 1.410 to the negative 4 is the Ka value. All right. They do ask you this on AP questions. But again, what they will do, they probably will, if you can do all of this I just showed you, you'll pass that question on the AP. Yeah, for sure, you will. Because probably they will say, write the Ka expression, that'll get you a point. Or they might say, write the equation, Or they might say, the first thing they might say is, write the Ka expression. And they might say, what is the molarity of C3H5O3 at equilibrium. And you'd have to do all this math here and get that. And of course you'd have to get those two. Then you get what's the Ka value. A lot of times they'll just ask you for one of these. So, you have to do all the work, but, they'll know, hey, if you know that, well then obviously you knew that, so that might be worth like 2 points or something. So you'll be in good shape. Okay, one more problem. I know it's a longer one, but I'm trying to do every kind of problem. Well, this is like, I'll tell you, and I kind of mentioned it before, everything I'm showing you right now, if you can do this, and you look at some old AP question, from the past 15, 20 years for sure, maybe even older, you're going to pass that question already. But now there's another big important thing that's going to happen that is going to come up in the next later on lessons. But I'll just show you. Okay, but this is a pretty good one here. All right, and here's the last problem, letter, if I can read it on mine here, F. It says the pH of a 0.063 molar HOBR solution is 4.95. Calculate the Ka. All right, pH equals 4.95. Yeah, I am going to do, I'm going to do the icebox. I always say do the icebox, so here I go. HOBR, I'll do this with a shortcut. I'll do the H plus, OBR negative. Now you might think, hey, I've seen OCl before. What is that? Hypochlorite? Guess what? That's probably hypobromite. Hypobromite, hypochlorite. A lot of times you can see it, if you know your polyatomic ions, you see another one that looks like it, ClO4. If you see IO4 negative, oh, that's periodate. Perchlorate, periodate. So a lot of these you might figure out, even though they might be seen like I never saw it. But it doesn't matter if you don't know it, you can still do it. Icebox, 0.06300 minus x plus x plus x, 0.063 minus x, x and x. Now, since they tell you the pH is 4.95, you know that from that you can get the H plus. Because remember, there's an equation that says, and this is not written on the AP formula sheet, by the way, H plus will always equal 10 to the negative pH power. Now, there's another equation I showed you before, equals the anti-log of the negative pH. If you wanted to use that one, you could too, but this is probably easier. 10 to the negative pH power. So H plus equals 10 to the negative 4.95 power. So I'll just, on my calculator, there's a couple ways you can do it. You could do 1 times 10 to the, oh no, I can't put 495 there. So I got to use the button that says x to the y. So I'll go 10 x to the y 4.95 negative. The 10 to the negative 4.95 power, and it says 1.12 10 to the negative 5. Now my sig figs, yeah, it could be, remember, you count 2 sig figs. You count after the pH. For a pH value, you don't say 3, there's 2. So 2 sig figs, so it's 1.1 10 to the negative 5 molar. All right, I'll double check that again. 10 x to the y 4.95 negative is 1.1 10 to the negative 5 molar. Okay, now what I'm going to do, at equilibrium, let's find them all out. I made a big mess of my poor little icebox here. So H plus is 1.1 10 to the negative 5. OBR is 1.1 10 to the negative 5. And look how small that number is. I don't even know if it's going to show up. 0.063 minus 1.1 10 to the negative 5. I always do it that way. It becomes 0.063 minus, I'll just write it that way this time. You can expand it if you want. But anyway, it ends up being 0.063. It stays the same. That's a great way to show you that why it's definitely negligible. That is so small. It doesn't. It changes it. It becomes 0.06299. So 0.06299, I would round it to 0.063 because I can only have 2 sig figs in it. So it becomes the same thing. You are meaningless. Look at that. You nothing. You're so insignificant. That broke off. That's why you're allowed to say assume x is negligible. So over here, oh, I didn't even write it yet, but okay. So We want to kind of find the Ka value, right? Yeah, Ka is H plus OBr negative over HOBr, which is 1.1 10 to the negative 5 times 1.1 10 to the negative 5 over 0.063. And if you're going to read that craziness, 1.1 to the negative 5, it looks like, wait a minute, that's got to be wrong. 1.1 to the negative 5. 0.063. Yeah, 1.9, I just typed the wrong number on my calculator. 1.9 times 10 to the negative 9 will be the Ka value. All right, hopefully I did all my math correctly here. I'll just double check. Yeah, 1.9 10 to the negative 9. I mean, maybe depending on how you rounded some of these, you might get 2.0 10 to the negative 9. I don't know. I think mine was 1.9. 1.9 or 2.0 are okay, but 1.9 10 to the negative 9. And if you want to make that a box, I guess it looks neater with a box. With a mess I've got there, though. I don't really box these very much. Oh, no. I'll put it underneath the equation. Okay, so, yeah, it's a lot of problems to do. So, 2 and 48, 7, 8, and 54. Because I'm having you do, one of them is very short and quick, but I'm having you do pretty much one of each type that I showed you. So, I will see you later on. We're getting along. We're getting there, getting there.